Hi, and welcome to my lesson presentation for Chapter 9, Geometric Figures. On our first problem, we are looking at these two parallel lines, and we have two intersecting lines that run through our parallel lines. So our green lines are parallel. And then in this shape, we're given numbers of angles, and then we're given two measurements of angles. So we look at this and we first say, okay, where do we even begin? We're supposed to find out all the measurements. Where do we start? Well, the easiest place to start is right here in this middle central triangle. And the reason is they give us two of the measurements for two of the angles. And what we know is the interior angles of a triangle are always equal to 180 degrees. So measurement of angle 7 plus 63 degrees plus 61 degrees is equal to 180 degrees. So that means our angle 7 is 56 degrees. Then we're going to look at angle 11 because, as you can see, it's on a flat line or a straight line, and a straight line is 180 degrees. So when we look at that, angle 11 plus 56 degrees is equal to 180 degrees. Therefore, angle 11 is 124 degrees. Then we're going to look at angle 12. Well, angle 12 is vertical to angle 7. Angles that are vertical are also congruent. So that's what that symbol. Angle 12 is congruent to angle 7. Therefore, in the symbol with the 3 blue dots, that means therefore. Therefore, angle 12 is equal to 56 degrees. Then we're going to look at angle 8 is congruent or vertical to angle 11. And since they're vertical, they are congruent. So it's also equal to 124 degrees. Then we're going to move to the left, and we're going to look at determining the sum of all these angles. Well, angle 9 is vertical, so therefore it is congruent to the angle measuring 61 degrees. Therefore, angle 9 is also 61 degrees. Then we're going to look at angle 6, because angle 6 and the measurement of 61 degrees, the angle with the measurement 61 degrees, together is equal to 180 degrees because it's on a straight line. So that means angle 6 is 119 degrees. Well, angle 6 and angle 10 are vertical, correct? Remember, they're across from each other. Therefore, they're going to be congruent. So angle 6 is congruent to angle 10. Therefore, angle 10 is also 119 degrees. So next, we're going to go to that top set of angles. And here we see that the 63 degrees is given for a measurement of one of the angles, that interior angle, the interior of the triangle. Well, we know that angle 2 is vertical to the 63 degrees. Therefore, angle 2 is also 63 degrees. Well, now we can look at angle 3. And angle 3 is congruent with angle 9. And if you see, even though they're on different parallel lines, they're vertical from each other. If you look here, this is angle 9, this is angle 3, and they're across. So angle 3 is congruent with angle 9, which is 61 degrees. We can also do that with angle 1 and angle 12. So angle 1 is also 56 degrees. Then we're going to look at angle 5 is congruent with angle 1. So angle 5, therefore angle 5 is 56 degrees. And for angle 4, it is congruent with angle 3. Therefore, angle 4 is 61 degrees. Now, we're looking at this large triangle within the, I tried to make it so that you could visually notice things first. The first thing I would notice is this large triangle. And what we know is in a large triangle, the sum of all three interior angles is going to be equal to 180 degrees. So here, we're going to go ahead and look at that, at the triangle as a whole. Forget about the lines on the inside of the triangle. And we're going to look, once again, our sum of those three angles is going to be 180 degrees. So when we're looking at that, angle 1 plus 74 degrees plus 26 degrees is equal to 180 degrees. That means angle 1 is equal to 80 degrees. Then we're going to look at angle B, which is 26 degrees. So if we noticed, and I'm pointing like you can see it with my finger, angle B, which is 26 degrees, is congruent with this angle 4. Therefore, angle 4 is also 26 degrees. Then we're going to look at, here we have angle C is 74 degrees, and that one is congruent with angle 6. And angle 6 is equal to 74 degrees. Then we're going to look at angle 1, and we know that it is congruent to angle 3, which is 80 degrees, so that one's also 80 degrees. Angle 1 is also congruent to angle 5, and since angle 1 was 80 degrees, angle 5 is also 80 degrees. Another way we could also get angle 5 is 4, 5, and 6 are on a straight line. So the sum of all three angles would be equal to 180 degrees. So if you add angle 4 plus angle 6 plus angle 5, you would get 180 degrees. So there's always that way. So angle 5 is 80 degrees. Then we look, angle 1 is congruent to angle 8, and that's 80 degrees. And then we look at angle 7 plus 80 degrees is equal to 180 degrees, because remember, angles 7 and 8 are on a straight line. A straight line is 180 degrees. So angle 7 is 100 degrees. Then we have angle 2. Angle 2 is congruent to angle 7. And since angle 7 is 100 degrees, angle 2 is also 100 degrees. Now we're looking at a concave polygon. Concave, we have two types. We have concave and convex. So we're going to explain it this way. In the bottom right corner, you see a convex polygon pop up in a hot pink. So when you look at this, you will notice on the convex polygon, all the angles point outwards. They're exterior angles. When we look at a concave polygon, some of the angles point inward. And you can see I have arrows pointing to where these angles come inside of our shape. So from here, we're going to use the n-2 times 180 degrees. What is n? N is the number of sides on our shape. So if in order to determine the number of degrees, a sum of all degrees inside our shape, we need to use this formula, n-2 times 180. Well, how many sides do we have? We have 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. So when we're looking at our formula, we're going to insert 8 where there's an n. So here we have 8 minus 2 times 180 degrees gives us 1,080 degrees. Then we have to take and get the sum of our angles. We're going to add each individual angle, and this is where I'm going with this. So here we see 3y, 7y. So what this is telling us, whatever y is, it's going to be 3 times our variable y, 7 times our variable y. Here we have 12 times our variable y. So we need to know this 1080, how many do we need to divide that by to get what y is? That's what we're trying to figure out, what y is, because we know whatever our variable y is, this angle is 3 times that. So when we add all of our y's together, we're going to get 54y. So that means we need to divide 54y by 54 to get y by itself. Whatever you do to the left, you do to the right. So we have to divide 1080 by 54, and that gives us y equals 20 degrees. So the next thing we need to do is now determine, okay, what does each angle, the measurement for each angle? Well, if our angle is 3y, that's 3 times y, so our angle for 3y is actually 60 degrees. Then we're going to look at our angle for 7y, and that one is equal to 140 degrees. And then our angle for 12y, which are those angles that point to the inside, those are 240 degrees. And in this case, if you would go through and write 60 degrees where the 3y is, 140 degrees where the 7y is, and then you go and add each of those angles together, you will come out with 1080 degrees. Next, we're wanting to determine the interior, exterior, and central angles. So once again, we're looking at, we need to use the formula n-2 times 180 degrees. In this shape, we have 9 sides. So we're going to do insert 9 for n, and n is our number of sides. 9 minus 2 is 7 times 180 gives us 1,260 degrees. So we're going to divide each side by 9. And that's going to give us y is equal to 140. And the reason I use 9y is because we have 9 interior angles. And each of these angles, they didn't give us, in the last shape, we had 3y, 7y, 12y. In this shape, it doesn't have a specific number, so that means it's all equal to 1. So I wrote it this way. The other way to do that is to write it here, and this is probably the more formal way of writing it. n-2 times 180 degrees divided by n. So that would be 9 minus 2 times 180 degrees, like we had up here, divided by the number of angles that are on the inside, or the number of sides, and that's 9. And it's going to give us the same y is equal to, or your angle is equal to 140 degrees. So the first thing we're going to do is figure out what is the interior angle. And you see a red line, a red arrow pop up. That's our interior angle. And our interior angle, we've already determined that, is 140 degrees. Next, we want to determine our central angle. And our central angle is in the center part of the our shape. Think of it as bicycle spokes. When you look at a bicycle, all the spokes come into a central point. That's what we're looking at, that central point where all the spokes come out. So in this situation, this central part, there's a total of 360 degrees. So for this one, we take our 360 degrees and divide by n. N is the number of sides on our shape. And that is going to give us a total of 40 degrees. Then we're going to look at our exterior angle. And our exterior angle is on the outside. And when we're looking at this, I want you to remember this. What we're seeing on these lines are line segments, right? It's just a small portion of this line. So theoretically, and our line can keep going. We're just looking at segments of lines to get a shape. If we extend this segment out further, we're figuring out the angle right here. This exterior angle is if we extended this line out. To determine that angle, what we know, it's 40 degrees. Because the interior angle, this whole angle right here, do not let this dotted line confuse you, because this was for figuring out the central angle. We know each of these interior angles, the total is 140, right? So this is 140 degrees. A straight line is a total of 180 degrees. So we look, the interior angle is 140. So if we continue, 140 plus what gives us 180? That is 40. So we know our exterior angle is 40 degrees. Next, we're looking at a tetrahedron. And I know I am doing this out of order, but mentally, it makes more sense for me to explain this and then go back to number 5. So a tetrahedron has 4 faces, or 4 sides. 4 surfaces is how I'm looking at it. So we have 4 faces. It has 4 vertices, which are the points, and it has 6 edges. So on a tetrahedron, what I want you to think is origami. On this particular tetrahedron, we have 4 equilateral triangles. So we take these 4 triangles and they're flat. So we're looking at, this is very simple. We're looking at flat triangles, and we want to think origami, and we're going to fold this thing to get a 3-dimensional shape. We're going to fold on each of these lines or edges. So these black lines are going to become the edges of our tetrahedron. And when we do that, we're going to get a shape that ends up like this. So this tetrahedron has 4 faces. My brain kind of stopped. And this is what I want you to remember. Look at it this way. The dotted lines, if you had this object sitting right in front of you, it's solid. So the dotted lines are the edges that we wouldn't see if it was sitting in front of us. Okay, that's the back side. So this is the back 3 edges. So when we count this, we count 1, 2, 3. And I know your brain's saying, but I only see 3 faces. Well, what you have to remember is we're looking through the first face like it's a window pane. So that first face is still there. So this whole outside triangle, that is face 1. Then on the back side, we have face 2, face 3, and our base. Your base is the foundation on which it sits or stands. So our base is our floor. So when we go back to the flat, viewing the flat surface, flat triangles, we see that purple is our base, is the base of our triangle, of our tetrahedron. And then each of the pink faces, or when we fold it up, that's what we're seeing on top. So that purple one we won't see if it's sitting on a solid surface. So that is a tetrahedron. Now, what we're wanting to do for example 5, for problem 5, is we want to take this tetrahedron and insert it into a cube. And a cube is a 3-dimensional object. So we take this cube, think of it like this. We have a diamond and we want to put it in a gift box. And inside that cube-shaped gift box, none of the sides of our diamond, and in this case our tetrahedron, our faces of our tetrahedron are not going to be flush or flat up against a face on our cube. So here we have our tetrahedron. So we have our 4 sides, and now we're going to put it inside our box, inside our cube, and there we go. So we see that certain angles, angle E, well, not angles. We'll take our line segment from D to E for our tetrahedron, and then we have E to G, E to B, B to G, E to G. So this is showing you all our faces on our tetrahedron and where our lines, and remember the dotted lines show us things that are further back. So in this way, none of our faces of our tetrahedron are flush or flat up against our cube. Next, we have an octahedron. So this one kind of blew my mind for a little bit. Think simply. Here, what is the first thing you see? You're looking at it and it's like, oh, that's a pyramid. Think pyramid. So a pyramid has a square base, right? And then it comes up with triangular shapes, 4 sides that are shaped like triangles. And this, again, is a solid object. Well, not only do we have the top, so we're thinking it's sitting on a shelf, and we have this pyramid sitting on a shelf. Well, with the octahedron, you got to add a second one. And this one is upside down. So they share that same, what we think of as base, is a shared surface between the two pyramids. And if you notice, there's 4 sides or 4 faces. What we consider the base, what we're going to call the base, it's shared, but it's not a face because it's on the inside. It's an internal spot. So we're not going to count that as a face. So there's a top 4 faces. There's a bottom 4 faces. When we put them together, this is what we're looking at. So from here, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8. And then we have here 9, 10, 11, 12 edges. So there's 12 edges to an octahedron. Then we have 1, 2, 3, 4, 5, 6 vertices or points in our octahedron. Next, we're going to look at an icosahedron, and this is the one that I love. Once again, we're going to think origami. We're folding these shapes, something flat. Remember, origami is taking paper, something one-dimensional, it's flat, and then we're going to fold it all up. So, in an icosahedron, we have 20 equilateral triangles in this case. And with our triangles, we want to fold this to make a 3D object. So the easiest way to explain this, and I'm going to show you, I took this is not considered a new triangle, I'm just showing you how we're going to fold this paper. So we have these 20 triangles, and then we take 2 different larger triangles. So when we're folding this, the 3 triangles covered by these large colored triangles, we're going to show we're not folding the 4 triangles in that area covered by that. Well, once we fold it, we're getting this. Isn't it amazing? Okay, on an icosahedron, we have 20 faces, right? So 20 flat spots, 20 triangles. So if you held it in your hands, you would be able to see 20 triangles. Then our vertices, or our points, there are 22 vertices. And then when we count our edges, so all these lines, we will have a total of 36 edges in an icosahedron. So I hope this helped you, and have a super wonderful day.